In the last segment, we looked at two possible mechanisms for an organic reaction, and by studying those mechanisms and comparing them with the experimental data, we were able to determine a rate law that matched an observed mechanism. In this example here, we're going to be doing effectively the opposite. We have an experimentally determined rate law and a proposed mechanism, and we want to see whether they are consistent, that is, whether they match. In this case, OCl- and I- are reacting to form OI- and Cl-. In a sense, this looks a little bit like the last reaction we saw. Two reactants going to form two products. However, the experimentally observed rate law here shows us that the rate of product formation is proportional to the concentration of each of the reactants to first order. That makes sense. However, when this reaction is run in basic solution, it's observed that increasing the basicity of the solution slows down the reaction. So let's look at the proposed mechanism to see if it can explain why that is the case. The proposed mechanism involves three steps. The first step is a fast equilibrium, but not necessarily one that favors the products, in which the OCl- is protonated. You might recall that this is hypochlorite and this is a weak acid. So this particular reaction right here is in a fast equilibrium. Once that has occurred, the actual exchange reaction can happen. This is the slow step, which again probably shouldn't be very surprising. We're breaking a bond between chlorine and oxygen and forming one between iodine and oxygen. Then at the very end, there is a second fast equilibrium, and in that fast equilibrium, the proton is removed and we're left with our final product. Looking through this reaction set, you can already identify two things that are pretty important. One is if we were to add together these three reactions, we do get back our overall reaction. That is, this proposed mechanism does not suggest that there are going to be any reactants or products formed or consumed that are not up there. So that's good. Additionally, this mechanism includes hydroxide, and that's good because it explains why hydroxide would show up in the rate law but not show up in the overall mechanism. So now let's see what we can do to combine together these equations and their properties to better understand what they might be doing. So we need a couple of things. First, we're going to want the equilibrium constant for this reaction. And that equilibrium constant is one that we can be pretty confident in our ability to determine. And of course, water is not present in this equilibrium constant expression because it's a liquid. Okay, that's one. The next thing we want is a rate law for this second step because it's not in equilibrium. That is, it's reacting with a significant enough negative delta G that we're really just transforming everything into this state. Now, we've seen that our concentration is going to be dependent linearly on several of our reactants that are present in this step. So it's a reasonable guess that we can describe them in that way. So we're going to describe this in terms of the formation of the product in that reaction. Now this is kind of convenient because that formation, given this fast equilibrium step that's taking place, any HOI that forms is going to instantly be converted to OI minus. That means that this rate is equal to the rate of our final product, and this is going to be equal to that reaction rate constant times each of the two reactant components here. So we now have a couple of components that we can combine together. Now, how do we go about putting these two together? That's a little bit weird, right? We have an equilibrium constant expression and a reaction rate law. It's not obvious that they should be allowed to be put together, right? But fundamentally, both of these are just mathematical equations. And they're mathematical equations where the same variables appear. That is, the concentration of our HOCl appears in both equations. So let's rearrange that KEQ so we're going to multiply both sides of the equation by the inverse of this. That will cancel it out on this side, and when we multiply it over here, it will give us our KEQ times those values. So now we have something that we can substitute into here. So let's rewrite that rate law now with that substitution taken into account. So we're going to take all that stuff in blue up here and put it down here. This now has some set of constants with OCl minus and I minus in the numerator and O minus in the denominator. So this substitution and what we get from it confirms that the rate law we've observed is indeed consistent with the experimentally observed rate law. By which I mean the proposed mechanism's rate law is consistent with the experimentally observed rate law. But we also get something more. Up here we had some experimentally observed rate law constant, and down here we have two constants now. That must mean that those two constants are equal to one another. Our experimentally observed rate law constant is equal to the rate law constant of this slow step times the equilibrium constant of the first step. Let's think about what that means for a minute. This is how fast the reaction is happening overall, and it says how fast the reaction is happening depends partially on the rate of the slowest step, that is the rate determining step. That makes sense. It also says that it depends on the equilibrium position of this first step. Remember, a equilibrium constant that is bigger favors the products more. If there are more products in this first step, the concentration of HOCl for this second step is effectively going to be larger. That makes sense in this context. A larger equilibrium constant favoring the products provides more to speed up the reaction in this second step. So this is an example of how we can combine together equations to determine an overall mechanism rate constant. This is about the most challenging example of this kind of problem that you'll be asked to do in this course.